Okay, hello everybody. We're going to be doing a predicted paper tonight. Now, I'm going to say this multiple times throughout the session. I don't think that you can predict what's coming up in the exam. The only way to do well is to know everything across all parts of the course and expect anything to come up. However, this one here, it's called a predicted paper. It means that you're watching it at the moment. People love the word predicted. And this one came from PMT. So I have not written these. I had a quick flick through the paper earlier. And actually, looking at the paper here, I would say it is better than what they did last year. So it's been put together by Latoya. I don't know them. If you're watching, hello, I suspect you might be at some point if you hear about this video. But I think that these are a good set of questions. I don't necessarily think that these are exactly going to come up, so you cannot rely on this to be your only bit of revision. Instead, just do all of the past paper ones if you're doing AQA physics, and that's going to give you the best chance to kind of get ahead. Also, by the way, I will be doing as it says under here, I'm going to be doing a revision masterclass this Sunday. I'm going to be doing an OCR one in the morning, then I'm going to be doing an AQA one at 1:30, which I guess is what you lot like, and then I'm going to be doing an EdXL one at 4:30, so that's all on Sunday. And to book them, all you need to do is go to A-Level Physics Online. So basically, if you go to my website, hopefully you've been there by now. I've got a couple of videos about A-Level Physics. But basically, if you go to classes, you can then book onto things that I've got coming up over the coming weeks. And a lot of you came along. I had about 900 people sign up for a revision masterclass I did last weekend. But basically, on the 17th, if you click on AQA Paper 1, you can book onto the masterclass, and it's a 2-hour-long session where I'm going to go through some of the main topics, the kind of the big misconceptions that students often make, a bit of exam technique and so on. So yeah, hopefully it'll all be good. Somebody says, get on with it. Okay, Ems, I'll do that. So let's just start with question number 1. So this one here is often the way that I've seen paper 2s begin. They've got something about particle physics. They tend to go kind of in order of where they come up in the specification. Complete table 1. So we've got a kaon, we've got a muon, and we've got an anti-muon neutrino. So a kaon is made out of 2 quarks, so it's not a lepton, so it's got a number of 0. The muon is going to be a lepton, so that's got a number of +1, and the anti-muon neutrino has got a number of -1. And then we've got the strangeness. Well, that's got 1 strange quark, and so I guess with a bit of a quirk of the way that we do kind of strange numbers, if it's got 1 strange quark, it's got a strangeness of -1. And these two things are both fundamental particles. There's nothing strange in there, so they're going to be 0 and 0. So first of all, that's what we start with. Okay, is this being recorded? Good question, Gibbo. Yes, it's going to be recorded on YouTube, and so once the stream finishes, you can re-watch it again and again, or you can just skip forward to the question that you need support with. And normally, I don't know how many people are watching this at the moment, but there's going to be a lot more people watching the stream, probably 1,000 people over the next few days. All right. Explain how we know that the strong interaction is not responsible for this decay. So I definitely think it's worth sometimes, if you've got a highlighter, highlight the words which are in bold so you actually answer the question that it's asking. And I guess what we have here is strangeness not conserved. So strangeness is not conserved. And then what that means is strangeness not conserved, but in a strong interaction, it must be conserved. And I guess therefore what we've got here is something where we've got a weak interaction because strangeness is not conserved. So that would be my answer. I'm not actually sure what the mark scheme says. Somebody says here, and by the way, in the chat, just let me know if you've done this paper already or not. Just say yes if you've done the AQA predicted paper, or no if you haven't done it. Right then. Because leptons are present in the decay and leptons cannot be present in the strong nuclear decay, I guess that's true. Okay, so yes, yes, no, yes, no, no, yes, no, no, half, no, yes. Okay, so I think it's useful. Some of you might be very familiar with the questions, and again, that might just really help you when you just see a different approach to it. The main thing, though, is when you're writing stuff in physics, keep it as brief as possible. The paper on PMT, you basically you basically go to the PMT website. They've got some extra resources, and you basically have to sign up, which is free to do so, and then you can download it. The marks do seem a little generous at times, but of course that's just because on a real paper there'll be a whole team of people actually going through the marks and things like that. So this one here, just take it as some sample questions of the kind of thing that often come up in exam things. Okay, right then, so the next question, using the rest mass energies of the particles involved in this decay, show that the total kinetic energy released is approximately 6 times 10 to the minus 11 joules. Okay, so basically, the first thing we can do is we can look at the change in energy from start to finish. And so basically the change in energy is going to be equal to the initial value, which is 493.821, take away the final value, which it gives us here as 105.659. And I guess what I haven't done is actually work any of this out. It's all going to be recorded, so if you do want to come back to it tomorrow or later in the week, then you can do so. Therefore, that's going to be 493.821 minus 105.659, which is equal to 388.162. And the units for that are going to be mega electron volts. And what we then need to do is convert from mega electron volts into joules. So the conversion is going to be 388.162 divided by 1.60 times 10 to the minus 13. The reason being that you should remember that 1 electron volt is 1.60 times 10 to the minus 19. But if we've got a mega electron volt, that's going to be 10 to the minus 19 times 10 to the 6, which is 10 to the minus 13, which gives me a number equal to, oh sorry, I've done that the wrong way around, isn't it? It's not divide, it's going to be multiplied, isn't it? Sorry, back up one sec. Is going to be equal to 6.21 times 10 to the minus 11. Okay, sorry about that. By the way, I'm going to see that there's going to be a lot of people correcting me, so please do that. So yeah, Macy says multiply. Garland says multiply. Yeah, so not divide, we multiply that. But of course, we see that. Now, the reason is that what we have over here is the rest mass energy. So that's the initial energy of that particle due to its mass, and that's the final mass of that thing. And basically what's happened is the change in mass has basically caused us to have a change in energy. And of course that energy is going to be, it's not going to disappear, it must go somewhere, and in this case it's going to be in the kinetic energy of the products from that reaction. Okay, now what I've done here is, because we've got a show question, you always need to give your answer to two more significant figures than what we've got over there. So I've got 6.21, which is approximately equal to 6 times 10 to minus 11 joules. Okay, so it's always good to give your final answer, maybe underline it so it's very clear for the marker, to at least 1 or 2 more significant figures. Okay, right, it says here the muon antineutrino released in this decay is effectively massless. Explain using conservation of momentum why the kinetic energy released is shared between the muon and the muon antineutrino. Okay, so it says in the question that, where does it say that? it says why the kinetic energy released is shared between the muon and the muon antineutrino. Okay, so maybe I don't... This is a bit more of a tricky one. So this is going to be the rest mass. So the initial energy is due to the fact that this kaon is not moving. So basically, the kinetic energy of the kaon is equal to 0 at the start. And therefore, its momentum is going to be equal to 0. Now, if I was writing this in my real exam next week, which I'm not, I would be doing this more as like a full sentence. But basically, the kinetic energy of that kaon is 0 because we've only been given its rest mass at the start, and therefore its momentum is 0. And therefore, because of the conservation of momentum, therefore, due to conservation of momentum, the total momentum of the muon and anti-muon neutrino is also equal to 0. So effectively, this is it beforehand. We've got the kaon. Afterwards, as much as the one of them goes off in one direction, the anti-electron neutrino must move off with a similar momentum in the opposite direction. Okay, and I guess therefore the kinetic energy released is shared between the muon and the muon antineutrino. Now it doesn't say equally, but if both of these particles are now moving at a certain velocity, they will then both have their own value of momentum. So the total momentum of the muon and anti-muon neutrino is 0. Therefore, they are both moving. So we'll both have a momentum in opposite directions. Do you know what? It's really difficult actually writing stuff out in a live stream because it's kind of the thing, it's very hard to kind of talk and write at the same time. Right. Somebody says you need to revise for GCSE. Will this help? If you're doing GCSE, no, what you need to do, sorry, did that not make any sense? They are both moving, so we'll both have a momentum in opposite directions. Now, of course, the momentum of the muon is going to be equal, its momentum is going to be equal to m times v. If you've got a neutrino, which is effectively massless, we can't use the same equation for this, because if it's effectively massless, it must travel at the speed of light. So v is kind of like quite a big number. But there's another equation that we don't have to use at A level, where we can basically relate its momentum to other properties of that particle. Where's my brilliant assistant, Joe? By the way, everybody in the chat, if you say hello to Joe Cattermole Tutor, he was here in my live stream, my revision class I did yesterday morning. Joe's running maths sessions. So when you go to my website and you can see that there's things to book, you'll see, for example, that on Saturday there's a maths revision session. So Joe, who's in the chat at the moment as Joe Cattermole Tutor, say hey Joe everybody. He's going to be doing a session for Edexcel A-level maths. He's going to be going through a paper 3 on Saturday afternoon. So he's going to be doing that. You can book it through my normal A-level physics online website. He'll be in the same studio where I am at the moment, but he'll just be doing a maths session. So basically, there we go. Yeah. Can I get on with it? All right, I will. Okay, let's get some more maths in here. Right, this one here. You might see the video, you might have seen it. We've got somebody who goes down a certain height, they take off, and then they go down a slope as they're ski jumping. Using the initial height of the ramp as 100 meters, which is what we have over here, determine an estimate for the initial takeoff velocity of the jump Vj over there. So what we're going to think about is here they've got a store of gravitational potential energy, and here that is going to be transferred to the kinetic energy store. So if we know that the potential energy is equal to the kinetic energy, we can say that's equal to mgh, which is equal to a half mv squared. And rather nicely, this means that the m's cancel, and in order to work out a value of v, we can just say that v is equal to 2gh square rooted. Okay, so that's all I'm going to do. I'm going to write down where this comes from. I've written down the equations, cancel something, rearranged, and therefore that's going to be equal to the square root of 2 times 9.81 times 100. By the way, let me know if I'm doing this right. I haven't done the CO2 stomach gas question yet. No, I haven't. But I don't know the answer to that really. Okay, so let's work this out. So 2 times 9.81. This is equal to 44.29. So I'm going to say that that data is to 3 significant figures. So I'm going to estimate this, that's going to be equal to 44.3 meters per second. So that is my approach. 3 significant figures there, 3 significant figures there. Now, you don't need to know the angle of the slope. All you need to know is effectively at this point they've only got kinetic energy, because here, sorry, they've only got potential energy because initially we'll assume that they start at 0. So ski jumpers, they basically just sit on their little step, they just kind of lean forward and then they just start getting faster and faster. So here the kinetic energy is equal to 0, and then we'll say that like this bit here is like the kind of datum point, and at this point their relative potential energy is going to be equal to 0. So all of that potential has gone into kinetic. Okay, you could have used suvat for the vertical, potentially, because effectively that looks like v is equal to the square root of 2as, which looks like a suvat equation. It has been estimated that the vertical drop after the takeoff is 260 meters. Using the information in figure 1, show that another estimate for the initial takeoff velocity of this jump is about 18 meters per second. Okay, so for this bit then, what we're going to think about is the second part of the jump when they move through something like this. So that's basically the parabolic path they're going to take because they are now undergoing projectile motion. Okay, we know that the vertical distance is 260, and we know that the distance they actually travel, it says, is 291, and we want to know effectively what is this value here, which we'll call Vj. Okay, now really that diagram should be much bigger. It's not particularly great. So basically this thing here is based on what we have on this diagram over here. Okay, so I've kind of just drawn that like that. So my approach to anything like this, all we need to do is write down suvat. And first of all, I'm going to consider suvat in that vertical direction. So we know in the vertical direction, they fall a height of 260 meters. Okay, we know that in the vertical direction, initially u is equal to 0. We know that their acceleration down is 9.81 meters per second squared. And we don't know, so that's meters per second, and we don't know the time. But what we can do is, knowing 3 of these, we can work out the 4th thing. So we're going to use a suvat equation without a v in it, and that's going to be s is equal to ut plus a half at squared. So that's the equation without a v term in it. And like most of the time, this bit here goes to 0 because u is 0, and we want to work out t. So we can therefore say that t is equal to 2s over a and the square root of that. So that's all I'm doing at the moment. Okay, so we don't need to know the angle at the moment. We're just going to think of this as projectile motion from here to here. So basically, this dotted line here shows where that ski jumper actually goes. So the time it takes is going to be 2 times 260 over 9.81. We're going to square root that, and that is equal to 7.281 seconds. Okay. Now the other thing we can think about is their motion horizontally. Now you could write this down as suvat as well, but what we want to know is how far they go horizontally. We know that their value for u, their initial velocity, is going to be equal to Vj, which is something that we don't know. And the time that they take is going to be the same time that we've worked out over here. So the time to fall is going to be the same as their time to travel along. And therefore, this time must be equal to this number, which is 7.281. Now, in order to work out the distance they travel, well, it's going to be this distance along here, s. Okay, and we can do that simply by using Pythagoras, because all we've got now is a simple right-angled triangle. So the value of s is going to be equal to 291 squared, take away 260 squared, we're going to square root that, and that's equal to 130.69. And so now, the speed that they're going at, Vj, speed is just simply distance over time, and in the assumption we're going to make is horizontally, there's going to be no air resistance. Okay, so is this all making sense at the moment? Right. Somebody says that they printed this out and extended the paper by 7 full pages of ads. Yeah, basically, look, I'm going to be doing masterclasses, and the masterclasses I'm doing, the money from that is allowing me to like have this office, to be here in the evening, and kind of, you know, the printing, the kind of computer, all that good stuff. Just like PMT, they're doing this thing for you for free, in hopefully to kind of get people like you to kind of sign up for their masterclasses as well. So yeah, there we go. Right, so this is going to be equal to the distance travelled over the time, which is 130.69 divided by 7.281, which is equal to 17.95, which is approximately equal to 18 meters per second. Okay, there we go. So there we go. That one there was just a different method of working out the value for Vj. All good so far? So it's a go. Thank you very much. Right. In reality, their velocity was measured to be 29.7. One thing I would say is that in real papers, we always use like a superscript there to kind of show meters per second. Discuss how the estimates from questions 2 and 1 compare with this true value. Be sure to include reasons for the discrepancy. So why is that? So I guess we've got a 4-mark question. So I see this as 2 separate 2 markers. So don't think of it as one big mega question. Think of it as 2 different things. The first one is we've got the overestimate, and the second one is we've got the lower estimate. Okay, so the first estimate was too high, as it assumed all the initial potential energy was transferred into kinetic energy. Okay, so basically that's the assumption we've made, and therefore this is because we did not account, or didn't account, for friction, and I guess there's going to be the work done by friction along that slope, and there's obviously air resistance as well. Okay, so that one there is basically too high. The second one was too low, but basically it says in the question somewhere that where does it say it? Have I put it on the floor somewhere? Okay, the second bit here is it's been estimated that the vertical drop after the takeoff is 260 meters. Now, I don't think that's true, because if you look at how steep this slope must be, when people actually do a real ski jump, it's not that they're going down something that's actually that high. In reality, although the slopes seem quite steep, they're probably going to be something a bit more like that. And so this distance here can't be 260 if that's 291. That's much more likely to be something like 100 meters in vertical height. So basically, I think for this, the second estimate for the height dropped was too large. Therefore, the value of Vj calculated was too small. Okay, or words to that effect, basically. So here, I would say, right, let me... By the way, if anybody is offensive in the chat, all I'll do is just ban people. Okay, so yeah, basically what are people saying? Okay, I'm just going to put some people in timeout. Okay, so basically don't be angry in the chat. Let me just check something. Okay, right, so basically, yeah, all be nice to each other. It's only physics, all right? Anybody who's disrespectful or anything like that, all I'll do is just ban you forever. Right, yes, also the second could be too low due to air resistance. Yeah, so basically I think for that one, for the second paragraph, it's not really, it's not, again, I think basically the answer is too low, because they assumed that they dropped 260 meters, and that gave them quite a long time. So of course, we know that in that last one there, basically, in order to work out Vj, this was equal to the distance travelled divided by the time. Okay, and the time came from when we had that Suvat question, when they fell through a large vertical height. Now the reality is they'll have fallen through a smaller vertical distance, which meant we'll have had a smaller value of time, and if you had a smaller value of time, we'd have had a bigger value of velocity that was estimated. So because we overestimated the time that they were falling for, that gave us a lower value for velocity up here. Okay, yeah, this paper is for free on PMT. Right, this one here is an easy thing that you have to get right. So this one here, state the principle of moments. If anybody's watching this and you haven't already seen it, I do have flashcards on my website. So if you go to more, or if you go to whichever exam board you might be doing, I've got over 600 flashcards for AQA. And so all you need to do on my website is choose your exam board, AQA, choose your topic. I guess this is mechanics. And then you'll see that I've got a load of flashcards that explain all of these kind of definitions you need to know. You cannot afford to mess up the definitions. So the principle of moments basically says for something in equilibrium, the clockwise moments are equal to the anti-clockwise moments. Now for something like this, if you've got to state it, then you actually have to write it out. We've got people saying stuff in the chat. Gary, we've got Mr. Bombastic. For an object to be in equilibrium, the sum of clockwise moments equals the sum of anti-clockwise moments about the same point. Perfect, yeah. The clockwise moment is equal to the anti-clockwise moment to keep the system in equilibrium. Gary, perfect as well. So there we go, 2 excellent things in the chat. I would write this down if it was a real exam. Mary wants the beams to hang horizontally. Assume the weight of the beams are negligible. Determine the distance x in figure 2 and the weight of the fox to ensure this. So let's do this bit first of all. So we're just going to kind of simply think about this bit of the diagram. And if you've got a moments question, you should always redraw the system just so it's easier for you. So basically this is the system that we've got. We've got this distance x, and this distance here is equal to 0.040 meters. We've got a force down. I'm going to just do that as 1.50 newtons. And we've got this other smaller force, which is 0.50 newtons. Okay, and of course, the reason we had to state the principle of moments previously was because that's a clue for the later part of the question. Why are they hanging the animals? It's not a real deer, it's not a real badger. And to be honest, there's no way that I'd get close enough to a live badger to actually hang it up from something. Okay, can I zoom out please? Yeah, sorry, this is probably a little bit small. Is that okay? Right, so we've got this thing here, and if we know that the anti-clockwise moments about a point are equal to the clockwise moments, then we know that of course the moment is equal to the force times the distance. So we've got 0.50x is equal to 1.50 times 0.040. So let me just work out x. .12 meters, 0.12 meters, and I'm going to give that to 2 significant figures like the data that we've got that. Do I have a list of definitions for both papers? Yes, I do. I have got every single definition broken down by topic for the whole of AQA, and also I've got all the definitions that you need for the astrophysics, for turning points, for engineering physics and medical physics as well. Yeah. So this one over here, we're basically taking moments about that position there. Okay, so that's basically what we're thinking of as a pivot location. For the next bit, I'm going to do this in purple. What's the weight of the fox? And what does the fox say? Well, nothing, because it's basically just hanging here. So we're going to take pivots around this bit. This distance is 0.150 meters. That's 0.050. This is like a GCSE question. Now the total weight is going to be equal to the badger plus the deer, which is 0.5 plus 1.5, which is 2.0 newtons. And we're going to have a fox over here that I guess it's going to be a smaller force because it's acting at a larger distance. So we've got the fox. And of course, anti-clockwise is equal to the clockwise. So 0.050 times 2 is equal to the fox times 0.150. Does that make sense? So that's equal to 0.66667, and therefore the weight of the fox is, all of you say it with me, 0.67. There we go. How much are my flashcards? Good question. The flashcards, you can buy a PDF of everything for £24.99, bargain compared to the amount of work we put in to make them. You can also get them if you, or when you sign up for a premium plan on my website. So if you want all of them, you can view them online if you get a premium plan. But also, if you get a premium plus plan, which you only need for 1 more month, if you buy it today, it will last until paper 3 in about a month's time. And that means you also can download all of the PDF things as well. So it's all there for you. Right. Yes, old news. I know, but the kids still like it. Can you learn the flashcards in 8 days? Yes, you can. I reckon you could. Right. Mary builds the mobile and uses a fan to mimic wind changes to observe how the mobile behaves. the lower beam is no longer horizontal. So if the lower beam is no longer horizontal, it now looks like that, doesn't it? So we've got a deer. That's my deer. And then we've got a badger. They're like shorter, aren't they? Imagine it's more stripy. Okay, so is this thing here in equilibrium? Yes, it is. So discuss whether her claim is correct. Mary is incorrect, as the beam is not rotating. It is still in equilibrium, and therefore the anti-clockwise are equal to the clockwise moments. Okay, somebody says it looks like a giraffe. Maybe more like a llama, or maybe an alpaca, maybe. Okay. Yeah. Yeah, it doesn't state the... Yeah, so basically, if it stays like this, then the whole thing is still in equilibrium. It just means that this force is acting at a smaller distance, but proportionally this force is also acting at a proportionally smaller distance as well, and therefore the whole system is still in equilibrium. Okay, is that 3 marks? I don't know. I guess so. So Mary's incorrect is 1 mark. As the beam is not rotating, it is still in equilibrium, and therefore the clockwise and anti-clockwise moments are the same. I reckon that might be enough for 3. It's always hard to tell because it's not like this is an official mark scheme. I reckon that's good enough for this live stream. There's going to be no resultant force on it. Now there would have been a resultant force which would have caused it to move, but now in this particular time there's no resultant force on it anymore. Yeah, I guess the phrasing could have been better. It could have said that it stays at the same angle. So if this angle here, theta, is constant, then they are correct. Okay. Would you lose marks for writing answers in bullet points? Great question. No, bullet points are probably better than what I've done here. Bullet points are good. Always use bullet points. Right then, this one here, total internal reflection, often quite a nice topic. I quite like this one. So, state the conditions necessary for total internal reflection to occur. So, I guess this is where, if you're not sure, let me just grab something. Okay, I do have the full AQA datasheet here. And sometimes if you're not sure about something, then just, write down what it says here. So it says here, for example, that it says here sine theta c is equal to n2 over n1 for n1 bigger than n2. Okay, so that's what we know from the data book. And of course, you can use this to answer what's going on here. So for total internal reflection to occur, then bullet point number 1, the refractive index of the, I suppose it's a medium where the light is, the refractive index of the medium with, and of course total internal reflection, we tend to talk about light, but it could just be a wave. So the refractive index of the medium with the wave is greater than the external medium. And often what we're really thinking about is going from glass to air. So the glass is going to have a bigger refractive index than the air. And also the angle of incidence is greater than the critical angle. Okay, so basically this is like the boundary condition that's where the ray of light approaching that surface then moves along the boundary, so it is like a boundary condition. So for TIR to occur, theta must be greater than theta c. Okay, is that all right? Yeah, somebody said SGL03, angle of incidence must be greater than the critical angle, and refractive index of first material must be greater than refractive index of second. That's better than I wrote here, so SGL03, nicely put. Sketch the light ray emerging from the optical fibre onto figure 3. So this is the ray of light and it emerges here. So let's just zoom in. If you're going to draw a diagram, first of all, protractors can be really useful. If you haven't got a protractor, go and steal one from school in the next couple of days. And it's this position here where we're going to have that ray of light. Now, as it goes from this thing here and it's emerging, it's not going to be totally internally reflecting. We get total internal reflection here, here and here. And if that's the ray of light coming in, then the ray of light that comes out is only going to move a small amount, and it's probably going to do that. So draw it in pencil with a ruler, and I think this is what you would see. Something I did notice was that probably in the work solutions, that angle there was far too big. That's one thing I did notice this morning when I kind of flicked through it. So that's a better answer, possibly, than the one in the... that's kind of probably better, where still the angle of incidence is going to be smaller than the angle of refraction. Okay, right, there's going to be right angle triangles, so I'm going to, if this is the right angle, we're going to assume that this is the right angle down here, and so I guess we also have another right angle triangle up here. Okay, so we've got a ray of light being totally internally reflected at one side of a glass fibre and then refracting as it leaves the end. The angle of incidence at the glass air boundary is equal to the critical angle. The ray of light then enters water as it leaves the glass fibre. So, so what do we know? Let's just write stuff on this. Here, the water, N, is equal to 1.30. In the air, the refractive index is equal to 1.00. And it said that on the previous page that in the glass, N is equal to 1.50. So first of all, we're going to add stuff onto this. All good? Right. Okay, what do people say? Can I zoom out a bit? Sorry, yeah. Okay, how's that? Is that all right? Is that big enough to read still? Yeah, please zoom out. Optimus Prime, thank you. By the way, has anybody in the chat actually signed up to one of my masterclasses this Sunday yet? If you signed up on Sunday, just say yes, because it'd be interesting to know if you've actually signed up for the extra masterclass. Can I tutor you? I literally am tutoring you, Bank. So that's FFRJRO Banks, yeah. So Kyle has signed up to all of them. Free code. No free codes. I did, however, give away lots of free masterclasses yesterday. So 5 people got all the masterclasses for free because they signed up after doing my free masterclass I did yesterday morning. Yeah, I'm your last hope. All right, cool. Yes. So a few people have signed up. That's awesome. This is just like a little extra, little bonus, really. So this angle here is going to be this angle here. So what we know is that sine theta c is equal to n2 over n1. Okay, so basically let's call that n1 and let's call this air n2. So that means the critical angle is going to be equal to n1, which is 150. Is that right? Oh no, sorry. It's equal to... Sorry, I've been looking at the comments too much. So the critical angle is going to be equal to n2, which is 1.00 divided by 1.50, and it's going to be sine to the minus 1 of all of that. And so making sure that my calculator is set to degrees, 1 divided by 1.5, inverse sine of that, is equal to 41.8 degrees. So I'm now going to label this on here. So that's 41.8. And if that's 41.8 and that angle there is 90, then 90 minus the answer is 48.2 degrees. And what we can now do is use the equation that says n1 sine theta 1 is equal to, well, let's call this medium 3, is equal to n3 sine theta 3. And it's theta 3, this angle here, that we're going to try and find out. So basically I'm calling this material 1, this material 2 and this material 3. So what we know then is n1 is 1.50. We multiply that by sine theta 1, which is 48.2. And that's going to be equal to 1.30 times sine theta 3. So if I just work this out, this gives me an answer equal to theta 3 being equal to 59.79. Is that right? Am I doing this right, by the way? Are people in love? Oh my God. I've just seen the best name, I Love Physics Online, in Madagascar. No way. Isn't it going from the glass to water? Yeah, so we're going from this one to this one. So here we've got n1 is 1.50, n3 is 1.30. So this gives me an answer equal to 59.79. Is that right? So I reckon the answer is 59.8 degrees. Am I correct? Oh yeah, the reason that we've got 90 minus 41.8 is because here we've got air. So this position over here, N2, is equal to air. And so the critical angle must be 41.8 degrees. And therefore this angle here must be 90 minus 41.8. Is that right? Am I correct? I think... So the value should be, let's see, so we've got 1 divided by 1.5, sine of that, 90 minus that, and then we've got sine answer by 1.5 divided by 1.3. Oh, I've made a mistake. I rounded down too soon. So basically with the true values, this should be equal, theta 3 should be equal to 59.31, which is 59.3 degrees to 3 significant figures. So yeah, basically, I rounded down too soon. Oh wow, okay. 121KN2 says that your teacher recommended to watch me. Yeah, well, it's great to have you here. Guys, sign up to his Sunday masterclass. It says, I Love Physics Online. Yeah, good advice there. We all make mistakes. I reckon, to be honest, if I'd put 59.8, they'd have clearly seen I understood the physics. I'd have got the marks. But yeah, you should really use your calculator values rather than like your rounded down values. So point to note is don't round down too soon. Keep as many significant figures either stored in your calculator or written down for that final part of the answer. Okay. Okay. The question said the angle of incidence at the glass air boundary is equal to the critical angle, which I guess is not true, because really if that was the critical angle, then this ray of light would have come out at an angle of refraction of 90 and all travelled along there, if that was a strictly true physics. But it just says here that we're going to assume that this is equal to the critical angle, which is why we've calculated it. So yes, it probably would make the diagram inaccurate. But basically, look, don't worry about it. This one here, it's good. You know, these questions are good enough to practice. Your real exam, especially if you're doing OCR, if there's any OCR people here, they will have been checked multiple times by teams of people, and all of these little mistakes would have been ironed out. Okay, right, next question. Oh, right. Oh, hold on, have I missed something? Oh no. Yeah, okay. This one here, a doctor performing a gastroscopy. I've only ever read that. I've never actually had to say it out. So basically, somebody looking inside somebody pumps carbon dioxide gas into the patient's stomach to expand the organ and clear away obscuring fluids. The refractive index of the stomach lining tissue is approximately 1.35, whereas the refractive index of the carbon dioxide gas is about 1. Explain why using the low refractive index CO2 improves visibility of the internal stomach lining, focusing on the intensity of the light returning to the doctor's eyepiece. Somebody says, what prescription is my glasses? These actually, brand new glasses. I got them this morning. They are obviously identical to my previous glasses, but they're just a bit less bashed up. So yeah, thanks for noticing these. I can't remember what it is. It's like, I don't know. I basically wear them most of the time, especially when I'm in front of the computer or driving. But yeah. Right. We've got Z Physics in the chat. I think you're, Z Physics, you're doing master classes this weekend as well, aren't you? You're doing like a kind of a longer session. If you've already signed up to my master classes, do that first. If you want to do even more, Z Physics, Zelio Physics is here as well. He's got some master classes running as well at different times. Okay, actually, Z Physics, could you help me with this question? Because I don't know. I don't think it was a very clear question. The way I see it is, I see this as, basically, it's a bit like when you're looking underwater, it's like you don't get a clear image, because basically your eyes are designed, so this is your eye and this is your air. This is the air around the eye, and of course your eye is designed to take light and then it kind of refracts it onto the retina. Okay, when you're underwater, you're basically in a different medium. So this is the water and this is your eye, and as I understand it, because this has got a different refractive index, it's going to bend the light by a different amount, so it doesn't actually meet on the retina at the back of the eye. Okay, so that's what it should be like. This is what it's actually like. And that's why if you've got goggles on, you basically have your eye, you've got your goggle in front of it, and that means the ray of light kind of bends here, then it kind of comes in, and you get the normal air-eye interface, which means we still see like a clear image. Okay, so that's kind of what it's like when you're wearing goggles. And as far as I can tell, this question is a bit like, rather than having all the kind of liquid at the end of the imaging optical fibre, instead you have something where it's like it's going into air rather than going into like a load of liquid. So I would say that for this question, I think the question is saying basically the carbon dioxide gas means that this is the end of the tube in your stomach, and basically this is full of CO2, where it's got a refractive index equal to about 1, which is a bit like air, and that means any light that's coming into this, it's basically going to be going here the kind of way we want it to be, rather than being distorted a bit like when you're looking underwater without goggles. I would feel sick reading the question. You don't like reading about organs and fluids. Oh my god, well, if you don't like organs and fluids, do not watch my videos where I took apart an eye when I did stuff about eye and lenses and things like that. Okay, right. Yeah, I think that this question isn't I would say, from what Z Physics says as well, this is not actually on the specification, and therefore this question probably, basically, I don't think you'll get a question about this, because I think that this one here isn't really a good question about what's exactly on the specification. So I think it's kind of a bit beyond that. Should we just move on to another nicer question? Yeah, I guess it's application of knowledge. I guess, what's it say actually? It says here, this is what it says. I'm sure a lot of you have seen this. This is what their model answer is. So I'm just going to leave that there while I get the blue Lego man. Right, here we go. Somebody said the blue Lego man was looking lonely, so shall I put them there? Is that all right? Looking at the camera? Cool. I'll just put their arm up. I'm a 44-year-old man playing with Lego. Right, anyway. Yeah, is that all right? Yeah, so basically that's what it says. The various fluids in the stomach would refract the light in different directions from the source, so less light would reflect off the stomach lining, leading to a more blurry and dim image. Using CO2 gas allows the light to travel through one medium before being reflected off the lining to produce a clear and bright image. Yeah, yes, I am the Lego guy. Yeah, it's me, Physics Online, I do all the Lego physics. Right, so yeah, basically that's it. Also, I'm not Zed Physics' brother. A lot of people, when they saw pictures of us together, said that we look like we're related. So I don't know, maybe in the distant past somewhere, but we're not related. I'm the one that Mrs. T talks about. Hello, Mrs. T. Nice to see you. Right. Okay. Let's move on to the next question. So this one is standard. You have to know about electron diffraction, and ideally, you've all seen this with some kind of electron diffraction tube in the lab. So electrons come in, they're diffracted by the thin graphite film, and then on the fluorescent screen we see a diffraction pattern. Now the key thing is, electrons are accelerated because of their particle-like properties. They travel like a wave, and then they interfere with their wave-like properties, and then they behave like particles when we actually get them interacting with the phosphor coating on the screen. Okay, oh, here we go, right. So this one here, yes, this is the physics and maths tutor one. Explain how these concentric rings provide evidence for the wave nature of electrons. Basically, the pattern is a diffraction interference pattern produced by waves that are constructively and destructively interfering with each other. I guess what else can we say? There's probably more we could add than that. Here we go. Best teachers in the world, jointly between us. And then also Bison Maths. Okay, by the way, I can't do any exam advice in Turkish, but if you do understand Turkish or you want to hear Mr. Bison talking in Turkish with some exam tips, he just put a video up this afternoon, so that's well worth watching as well. Okay, right. Actually, Mr. Bison, where's he? Is he just on the beach somewhere sunning himself while I'm working in an office here? Anyway, okay. Right, that's basically what happens. So, because what we have is the electrons diffract by the regular lattice structure of the graphite. Okay, I probably could have written that a little bit better, but basically we've got electrons that travel with a certain velocity. At that velocity they have a certain de Broglie wavelength, which is similar to the spacing between the carbon atoms in the graphite film. We then get diffraction, and of course we then get the diffraction pattern where we have more electrons interacting at certain parts. And if we think about it like a diffraction grating, we get these kind of fringes that we might see on the screen. But of course, that's going to be in 3 or 2 dimensions, I guess. It's been like rotated around, which is why we see something like this. Okay, the fluorescent screen thing. Basically, the electrons collide with the atoms in the coating. And then what that means is an electron can cause one of the electrons in the fluorescent screen to move to a higher energy level. And then as it de-excites and drops back down to its ground state, it gives out a photon. So it's this bundle of energy that's then given out. So basically, the phosphor coating is energized. The electrons in this jump up to a higher energy level. As they drop back down, they give out some light. A bit like you might have seen, you know, if you excite something in a flame or with an electric field or something like that. Okay, is that all right? Right. Master plays. Do you need to mention that bright rays are constructive and dark rings are destructive? I think if you did that, that would definitely, yeah, give you the 3 marks. I suppose they probably should have had more lines here for a 3-mark answer. But yeah, I'd definitely say if it's a dark point, that's where you have destructive interference, or when it's bright, you have constructive interference. The initial speed of the electrons is increased. So what we know is that if V goes up, what happens to other things? Well, we know that the de Broglie wavelength is equal to... what's that equal to? No, sorry. The de Broglie wavelength is equal to hc over p. Is that right? Because the momentum is equal to hc over lambda. So, oh, is that right? Let me just check the way that AQA do this. AQA say, where is it? Oh no, have I done that the wrong way round? Ah, right, ignore that. Right, I'm getting tired. I've been going a while. Okay, if I've made mistakes, do let me know in the chat. We know that the de Broglie wavelength lambda is equal to h over mv. And what that means, if the initial speed of the electrons goes up, because the mass of them and h will assume to be constant, that means as they get faster, the value for the wavelength goes down. But we also know that we can use the equation that says for a diffraction grating, d sine theta is equal to n lambda. And if you've got a smaller value of lambda, bearing in mind n is going to be the same and d is going to be the same, as you decrease this, we're going to make sine theta smaller. So basically now we need to kind of sort of put that in some proper words. So this is where bullet points would be ideal. So, sorry, I love physics online. I didn't mean to ignore you. Can I make a video just answering hard electricity questions? I've got loads of videos about electricity questions, including all the ones from my daily workout books and loads of videos where I go through past papers, yeah. Right. We can't use C equals F lambda because that's more to do with the wavelength of a wave. Okay, so basically, as V increases, lambda decreases. As lambda decreases, sine theta decreases. And so effectively theta is like the angle apart that these things are. And if we're going to make that smaller, then all of these things get closer together. And that means the rings get closer together. Okay, so what you might see is that you see the rings sort of look like this. And as you increase the value of V, the rings kind of get closer together and they might look a bit more like that. Okay, so that's basically small v and that's a big V. Okay, right. And of course, yeah, I guess they're going to be circular. So effectively, if you think about from the graphite to the end where the rings are seen, we're going to basically have like the central maxima here, and then they're going to be sort of spread out like this. So basically this is like a top-down view, but what we see at the end would be a bright spot in the middle, and then we'd see a circular ring like this. And of course you'd also have something over here and something over here, which would be like the other ring over there. And so this angle here, theta, is going to be related to the space over here between the rings. Does that make sense? So yeah, smaller angle means a closer ring together. Good. How are we doing, everybody? Oh my God, there's just so many questions. Right, it keeps going. How's everybody getting on? By the way, for the people in the chat, can you just let me know yes or no? Have you actually seen electron diffraction in the lab in your school? Not on a video, but actually done by your teacher with some real equipment. So yes or no. Yeah, have you seen that experiment that we've just talked about with electron diffraction? So we've got no, no, yes, no, yes, yes as Z physics, no, yes, yes, no. Yeah, so surprisingly, actually, quite a few people haven't seen it. No, no, yes. Briefly with a laser and a grating. That's a slightly different thing with a laser, because with the laser and the grating, that's about the diffraction pattern with a diffraction grating with light. But this one here is more about trying to show that you've got this wave-particle duality, that things we always used to think of as particles actually travel like waves. We need a Lego version, maybe. Somebody, I love physics, your teacher calls you a risk for practicals. Okay, yeah, right, okay. Let's do the next bit. State the distance BD in terms of lambda, and hence work out the phase difference in radians between the waves at A and D. So it says here, we've got, do you know what? I wasn't showing the question, was I? Here we go. Let's show the question again. Right. What time is it? Is it nearly your bedtime yet, or are you allowed to stay up late tonight? If you want to stay up late, we'll do the whole paper. Let me just check my messages. Cool. Right. Good. So this triangle here, let's just draw it out nice and big. So we've got this triangle here. So that's going to be a right angle there. We've got A, B, and D. And it says, there we go, so that's basically just that triangle just drawn out even bigger. So diagrams are going to really help you. We've got a section of a diffraction grating with a grating spacing D. Blah, blah, blah. We've got a second order image. They've given that one there in bold. And of course, all of you need to know how to derive or be aware of how we actually derive the equation for diffraction gratings. If it's a second order image, then we know that d sine theta is equal to n lambda, but here n is equal to 2. So we can say that d sine theta is equal to 2 lambda. And I guess if we look at this thing over here, then this here is the hypotenuse, which is a distance of d. So that's the spacing for the diffraction grating. Not the lines per millimetre, but that's d. I guess this angle here is going to be theta. And then, of course, thinking about hypotenuse, adjacent and opposite, sine theta is equal to the opposite over the adjacent. And so the opposite side, because sine theta here is equal to 2 pi over d, so the opposite side must be equal to 2 lambda. So the distance BD is equal to 2 lambda. And the phase difference between waves A and D, I guess if it's equal to 2 full wavelengths, if that's the path difference, that's going to be the same as 2 wave cycles. And so the phase difference is going to be equal to 2 pi for one cycle multiplied by 2, which is equal to 4 pi. And that's going to be the phase difference. So the path difference must be measured in meters because it's a difference in path that things have travelled, whereas phase is going to be measured in either degrees or radians. Okay, how's it all going? Right. Okay, right. All good, everybody? Yeah, so that one there, nice, easy, 2 marks given to everybody. State the distance CE in terms of lambda. Well, actually, I guess effectively now we've got a distance here equal to 2d. We've got a similar triangle to what we had before. So that there was 2 lambda, so this must be equal to 4 lambda. So this one here, state the distance, that's just going to be equal to 4 lambda. So you don't even need to show any calculations if you're stating it. And then, am I right? I'm just checking I'm actually right. That seems good. Use your results in here to show that 2 lambda equals d sine theta for the second order image. I don't know how we do that, really. I guess I've already done it. So let me just draw that triangle out again. Obviously you need to be using a ruler to show that that's actually a right angle. We've got this distance here from A to C is going to be equal to 2d. That angle there is theta, and we know that from C to E is equal to 4 lambda. And of course, if I'm just going to write this on here, we've got the hypotenuse, the adjacent, and the opposite. And we know that sine theta is equal to the opposite, so opposite over hypotenuse. So we can say that sine theta is equal to this opposite side, 4 lambda, divided by the hypotenuse, which is 2d. So sine theta is equal to 2 lambda over d, and therefore d sine theta is equal to 2 lambda. Is that all right? Okay. So when he wants to go and eat ice cream, that's a very good thing to do. Right. Okay. Is that all right? Okay. Okay, how we go. Right. This one here. Oh my god, it just keeps going on and on and on. I reckon we'll be done by 10 o'clock. Is that okay for everybody? Yeah, that's a lot for 1 mark, but I think it's just more the time it took to write it down. So now we've got a potential divider circuit. We've got an EMF of a certain value, negligible internal resistance, which is always a nice thing. We've got a little treat for you all. They're connected across a light emitting diode, which has a PD across it of 2.5. So if you've got numbers here, just write them in. So that's 2.5 volts. And the question says, show that the PD across the 50 ohm resistor is about 0.5 volts. Okay, so if that's got 2.5 volts across it, we can actually read something from the table at 2.5. Now, a good way of doing this is always just making it very clear the data that you've got. So I'm going to use a ruler here, and I've got my set square to read off the value that we've got. Okay, and to show that I've actually read some data here, that value is 2.5 volts, which is the potential difference across the LED, and we can see that gives a current equal to 0.01 amps. Okay, so what we know then about that component is we know that I is equal to 0.01 amps, and that's across the LED. And then, of course, what we can start to do is put more data into here. So if we know that's 2.5 and we know the current is 0.01, we can now work out the PD across this. So we can say that V is equal to I times R. So the current, we've just worked it out, is 0.01. And the resistance is 50 ohms. And that's going to be equal to 50 of that, which is 0.50 volts. I'm going to put 0 volts to show that's one more significant figure than what we've been given up there. So there we go. Hopefully that's all good. Yeah, guest says, is it me or do some physics questions not make sense? Because there's a question asking about one thing and you need to use another equation which isn't mentioned. Yeah, that's just the way A-level physics is, so much more than GCSE. I'm just going to put some more people in timeout. Somebody said that they used to use this pen in year 6. Yeah, an amazing pen. So I'm going to add some more data here. So that's 2.5 volts. That's 0.50 volts. And of course, if that's 0.5 and that's 2.5, they add up to 3 volts over here. Okay, all good so far? If you're doom scrolling, you can just re-watch that bit. So basically, I worked out the current in that bit of the loop because we know there's 2.5 volts across the LED, which means it's got a current of 0.01. And we know that if there's a current of 0.01 through a 50 ohm thing, V equals IR, so we get 0.50 volts. Determine the EMF of the power supply. So I guess we know that's 3 volts across that, so we can now work out the current in this part of the circuit. So the current is going to be equal to V over R, and that's equal to this value of potential difference of 3 divided by the resistance of 75, and so here that's equal to 0.04 amps. So you've got 0.04 amps in that part of the circuit. And if you've got 0.01 here and 0.04, you must have 0.05 amps up here because of Kirchhoff's first law. And now we can work out the potential difference across that because V is equal to IR. So we've got 0.05 times 100 is equal to 5.0 volts. And now if we think about Kirchhoff's second law, the EMF is equal to the sum of the PDs around any closed loop. So that's 5 and that's 3. So that must be 8.0 volts. So that would be my answer. So determine the EMF of the power supply. If I was going to do this question, I'd have probably written out or drawn out the circuit diagram again. I'd have shown my working like this to find that the EMF is about 8.0 volts. All good? Right. I'm not related to PMT, but I've done some questions for them before. Actually, for those of you asking, I have done stuff with PMT, so you might find some work solutions on their website that I've put together. I also had loads of work solutions for their multiple choice questions for the AQA question packs. So I've done all of that. Right. A student suggests to use the circuit in a light sensitive system by replacing the resistor with a light dependent resistor. They argue that this will make the LED turn on when it gets dark. Discuss whether the student's suggestion is correct. So I'd have thought that any time you get a question like this, always use the space here to draw a diagram. So they're saying that we've got a light dependent resistor. So that's one of these. And that's still in combination with these other things that we had before. I'm just going to put the power supply like that. Okay, so that's my very quick sketch diagram. Right. How did I get 0.05? Basically, I worked out the current in this loop. I then worked out the current through that resistor, and the total current must be equal to this value plus this value. And if we know the current through this, we can work out the PD across it, and then the EMF is equal to this value of PD plus that value of PD. Okay, cool. Right, so if you've got a light dependent resistor, we also know that the resistance goes down when the light intensity goes up. So basically, if it gets darker, then the resistance is going to be going up. And if the resistance goes up, that's going to have a greater share of the potential difference than it did before, because that's going to be related to its value of resistance. So what does that mean? That's going to go up in terms of its value. So whatever the value of the EMF is, this is going to have a bigger share of that EMF, and this is going to get smaller. So it's going to be a smaller... Oh yeah, it's an LED, isn't it? Sorry. So we're going to have a smaller value of PD across the LED, and therefore it's going to be off rather than on. So let's just put that in bullet points. So as it gets darker, the resistance of the thermistor increases. This means, therefore, the PD across the thermistor increases, and therefore the PD across the LED goes down, so it doesn't light up, and therefore the student is wrong. Okay, so that's my answer for that question. Does that make sense? So basically, we're just thinking about, as we go around the circuit, if it gets darker, then the resistance of the thermistor increases. So that's going to have a bigger share of the EMF. And that means this is going to have a smaller PD across the LED, so it's going to give out less light. Sorry, LDR, not thermistor. Yeah. Okay. Sorry. I know that. I've literally drawn an LDR there. So as it gets darker, the resistance of the LDR increases, so the potential difference across the LDR increases, so the potential difference across the LED goes down, so it gives out less light. Is that all good? Thank you very much, Pilson, and everybody else there monitoring my my chat. Okay. Draw and label arrows in figure 9 to show the forces that act on the suitcase as it passes over the highest point on the humped-back bridge. So this is a great question, a kind of staple question that comes up all the time. If you're going to draw something, use a ruler and use pencil in case you make a mistake. So I'm just going to draw a circle to show the centre of that object, and I'm going to do an arrow down, and I'm going to do an arrow up that isn't as big. Okay, so the forces are going to be, the force down is the weight, and the force up is going to be the normal contact force. And basically the weight is bigger than the normal contact force, which means there's going to be a resultant force down, which means that we have the suitcase undergoing circular motion as it goes over the top of the bridge. Am I going to be doing a session like this for EdXL? Sebastian, I won't, because I don't think PMT have actually made an EdXL predicted paper. So that's the only reason I'm not doing an EdXL one. I'm just going to stick with the AQA one and maybe try and fit in an OCR one as well. Reaction force is also an appropriate answer. Yeah, that's absolutely fine as well. I call it the normal contact. Oh yeah, and actually they call it the normal contact force N in the next bit. So, determine the normal contact force given that the radius of curvature of the bridge is blah, 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 blah. So, let's do that again. The normal contact force N, and you've got the weight acting down W. And basically the resultant force is going to be equal to the weight minus this. And that's equal, I'm going to call that FC to represent the resultant force is equal to the centripetal force. Now, of course, we know the centripetal force is equal to mv squared over r, but we also know that this resultant force is equal to the weight of the suitcase minus the normal contact force. And basically what we can now do is we can equate the two things together to say that mv squared over r is equal to w, which equals mg, minus n. Everybody follow me so far? Yeah, reaction is fine. Normal contact force is fine as well. Yeah, by the way, if you're doing year 12 stuff, this is all useful stuff as well. Maybe not so much this, but yeah. Why is the weight greater? Wouldn't that mean the suitcase sinks in the seat? No. If the normal contact force was bigger than the weight, that's when the suitcase would sink into the seat. Basically, this is like the suitcase starts to lift up very slightly. Okay, right. So let's do some more stuff here. We want to find n. So n is equal to mg minus mv squared over r. Or we could say that n is equal to m multiplied by g minus v squared over r. Okay, so that's the equation I'm going to use. It also says actually here that the velocity of the car is 30 kilometers per hour. So the velocity is going to be equal to 30 times 1,000 over the number of seconds in an hour. So that's equal to 30,000 divided by 3,600, which is equal to 8.33 meters per second. All good? Yeah. Right, okay, so let's do the answer here then. So N is equal to the mass, which is 3 kilograms, times 9.81 minus 8.33 squared over the radius of 20. So I'll just work that out here. I'm hoping I'm doing the right thing. If I make mistakes, do let me know. This tells me that N is equal to 19.01. So that's going to be 19 newtons. That good? Is that right? Okay. Everybody good with that? So this one here, I've seen it come up quite a few times in previous things. Okay, I got the best production out of all the YouTube teachers. Also, by the way, what people don't realise is what's behind me is made out of Lego. So there we go. Right. Yeah, that bit there was like circular motion that we've just done there. So yeah, basically all of this stuff behind me is Lego. Shall I show that? So here we go. This thing here, all made out of Lego bricks if you look at it closely. Yeah, there we go. A lot of people have seen this for the last few weeks and not realised that it's actually Lego. And also, the oscilloscope is Lego as well. And even this, look, that bit there, bit of a meter ruler, all made out of Lego bricks. So yeah, it's nice to kind of be a bit of, yeah, I'm a grown man, by the way, but you know, I'm also a grown man and this is my job and I can make money by playing with Lego and doing a bit of physics. So yeah, it's not bad, is it? Right, okay. So, explain what happened to the magnitude of n if the car passed over the bridge at a higher speed. So, we've said here that the normal contact force is equal to m times g minus v squared over r. Okay, so what's going to happen is if v increases, then g minus v squared, so basically if v increases, v squared is going to go up, and that means g minus v squared over r, all of that is going to go down. Okay, so the bigger the value of v, this number here gets closer and closer to 0, and there's going to be a point where eventually n approaches 0. And at that point, there's now only going to be on the bag, there's going to be no normal contact force acting up, there's only going to be a force down due to its weight. And that means the object will then kind of actually move off the seat and start to sort of fly up into the air. Okay, so for this one here, explain what happened if the magnitude of n, if the car passed over the bridge at a higher speed. So if a car speed that exceeds 50 kilometers per hour, so if v is equal to 50 kilometers per hour, so you've got 50 times 1,000 divided by 3,600, that's now its velocity. If we square that, divided by the radius, 9.81, take away that answer, and multiply that by 3, then basically n is equal to 0.5 newtons, and at 50 kilometers per hour, the bag almost becomes weightless. So basically, if the car is bigger than 50, so if v is bigger than 50, then n goes towards 0 newtons, and therefore the bag, it doesn't have any force provided by the seat upwards, so the bag rises into the air. How's that? Is that all good? So this one here, I think, is a nice standard physics question. It'd be amazing if this came up. But yeah, so somebody says this is manipulated. Where is the formula on the formula booklet? Yeah, so the formula came from the centripetal force is equal to mv squared over r, and the centripetal force is the resultant force caused by the weight minus normal contact force. And then I did all of this, which is a kind of standard kind of A-level thing that can come up, to say that the normal contact force is equal to m times g minus v squared over r. Okay, right, now let's do some multiple choice. By the way, people playing along at home, I hope it's not past your bedtime, but what we can do is kind of play along. So if you haven't already done this so far, let me know if you got A, B, C or D. I think my voice is going as well, so I'm just going to have a quick sip of water. Okay, right. Which of the following has the smallest specific charge? So the specific charge is equal to the charge divided by the mass of that thing. So the first one, the charge is going to be 1, which is the number on the bottom. So that's related to Q. And the number at the top is related to the overall mass. And we just want to have the ratio of these two numbers. So all we need to do is 1 over 1, which is 1. This one is going to be 2 over 4, which is 0.5. This one is going to be 6 over 14, which is 0.42. And here we've got 92 over 235, 0.39. So not a full set of working out, but basically here D is the right answer. Kyle, Faizan, is that Joseph? All of you getting D, getting the right answer in there straight away. Nice stuff. Okay, so that first one, nice and straightforward. D, says Redders. Okay. The units can be... Okay, so units of quantities can be based in fundamental base units. Which line of the table are these correctly matched to the physical quantity? So all we need to do is just work out all of these and then see which of these are correct. So energy, if we think about kinetic energy is equal to a half mv squared, and therefore the unit of the joule can also be given as kilogram, and then you've got meters per second squared, so that's going to be meters squared second to the minus 2. So that's what energy should be measured in terms of its base units, and therefore this is incorrect, so it can't be that. Okay, somebody's saying C, right. If in doubt, go for B. I don't know. Right, potential difference. Potential difference is equal, where should I do this, over here? Potential difference is the energy per unit charge. And of course, energy we've just got up here as kilogram meter squared second to the minus 2. Charge is measured in coulombs, but that's also the same as current times time, which is amp second. So we can also give this as kilogram meter squared amp to the minus 1 second to the minus 3, and therefore that is incorrect, so it can't be that one. Right, power is equal to energy divided by time, so power should be the energy divided by time, which is kilogram meter squared second to the minus 2 divided by seconds, which is therefore kilogram meter squared second to the minus 3. So that one there is correct. So we think the answer should be C, as read as we've got Parshama, Joseph, Kyle, SGL, Bilal, all of you saying C as well. Yeah, that is the right answer. We can also see that charge should be current times time, so that should be amp second, so that's not true. Nice. Okay, so this one here is about the photoelectric effect, where we've got the energy of each photon is going to be equal to hc over lambda. That's going to be equal to the work function plus the kinetic energy. So that's Einstein's photoelectric equation. If the wavelength of the light is kept the same, then all of the other things are the same, so the kinetic energy is going to be unchanged. So it can't be B or D. Okay, what do we reckon the answer is going to be? Right, somebody says, would you save this live? Yeah, this live is going to be saved on YouTube so you can watch it multiple times. By the way, can I just say, everybody at the moment, if you haven't already done so, can you like the video? Can you do the heart button thing? So I think that's a nice thing. And can also you make sure that you do subscribe to me on YouTube, and also go and have a look at A-Level Physics Online. I've got a masterclass this coming Sunday all about paper 1, so it's 2 hours final revision just to help you prepare for next week. Thank you, everybody. Right. The number of photoelectrons emitted per second, well, that's going to be linked to the energy instant per second is halved. So if there's less energy coming in, that means the intensity goes down. So there's going to be less of these photons. So we're going to have less photoelectrons, and so that decreases. So it doesn't increase, and therefore the only right one must be A. Well done, people. You can do this, folks. Good. Whoa, I love this one. This is nice. By the way, if anybody isn't familiar with this practical, let me just show where you can find information about it. So if you go to A-Level Physics Online, my website, go to More and click on Practical Experiments. And this is all the practical experiments I've got videos about. And there's one here about Planck's constant, which is this page. So this is the Planck's constant thing. And I've got some notes that you can download where I actually go through different methods. Now, the normal method that if you're at OCR, you kind of tend to do this as one of your required practicals. Basically, you can do Planck's constant looking at different colours of light. But there's another way that you can do it using something called a vacuum photocell. And we know that HF equals phi plus Ke max. And what you do is you use different colours of light that you shine onto a surface, and then you alter the stopping potential. And eventually what you get is this graph over here. And you can use the gradient of that line to work out Planck's constant. Okay, so you can find that for free over A-Level Physics Online. All you need to do is go to More, go to Practical Experiments, and then you'll see at the bottom of the page, I've got this one here about Planck's constant. Okay, do you need to know all the practicals for paper 1? Yes, you do. Absolutely. Right, so what we've got here is we've got the energy of the photons is equal to the work function plus the kinetic energy. And if I rearrange this, we can say that the kinetic energy is equal to HF minus phi. Now, the important thing is we can write this in the form of Y is equal to mx plus c. Okay, we can see here on the y-axis we have the kinetic energy. On the x-axis we've got the frequency, and that means the gradient m must be equal to Planck's constant, which is why we've got the same gradient for both these bits of data. And the y-intercept is equal to minus phi. Okay, so let me just extend this line down a bit. So if we extend this further down, we can see that x stops there and the other one, y, stops down here. So we basically, I've kind of continued the data down to where it would hit that. So which of these is incorrect? So let's see which is correct. Below the threshold frequency, no photoelectrons are emitted. Well, that's going to be true for both of them, so that is a true statement. The gradient of both lines is equal to Planck's constant. Yes, it is, because we've seen that up here, and it's a constant gradient, because h is a constant. The work function of x is greater than that of y. So the work function of x here is greater than that. Oh, I don't know, what do you reckon? Is that right? Not all photoelectrons emitted from the surface of metal Y will be measured to have the maximum kinetic energy. That's true. Okay, that one there is a false statement, because basically the work function of x is going to be a smaller value, and this is going to be a larger value. So that one there is an incorrect statement, and therefore that is the correct answer. So well done, everybody. Yeah, this one here, it is a confusing thing. It's not often coming up, but And also it's very hard to actually do the practical with a real photocell because it just doesn't work most of the time, especially with the kind of things you might get at school. So therefore, yeah, that's a bit confusing, but the theory's all sound. So a lot of the time, you know, write out the equation in the way it's given on the graph and then see how that relates to the y equals mx plus c line. Okay. Which row, for number 12, what do you reckon the answer is? A, B, C or D? What gives evidence for the nature, the wave nature of electrons and the particle-like nature of light? So the wave nature of electrons is due to what we saw earlier about electron diffraction. So that's true and that's true. And the particle-like nature of light is due to the photoelectric effect. So for 12, AAA says red as, Kyle says A, Parshama says A, Macy says A. I'm just going to check a message. Just got a reply to a message. Okay, so basically for 12, all of you, Ish, Adam, EGL, all saying A. So there we go. That's the way that one there lands. Number 13. The diagram below shows the ground. I'm going to have to move the Lego guy. I'll keep his arm in the shot. The diagram below shows the ground state and 2 higher energy levels for an atom. The transition from X to the ground state produces a wavelength of 130. So this one here is 130 nanometers. And Y is going to be 165 nanometers. Okay, so what equation can we use? We know that the energy is going to be equal to hc over lambda. So we could basically just work out the energy for each of these. So for the first one, we've got 6.6, let me just check, 10 to the minus 34, isn't it, for H? 6.63 times 10 to the minus 34 by 3 times 10 to the 8 divided by 130 times 10 to the minus 9 is basically 1.53 times 10 to the minus 18. And we're going to do the same for this. 1.20 times 10 to the minus 18. And so the change in this case is going to be 3.24 by 10 to the minus 18. And for things like this, do the maths just like a normal kind of question. Don't look at the bottom, at the numbers, just do the maths, see what the answer might be. And here it's about 3.2, times 10 to the minus 19. I didn't even read my calculator properly, and therefore D is the right answer. Right, so okay, what are people saying? If you have a school subscription for my website, can you use the flashcards? Yeah, so basically, if you've got a school subscription that you have on my website, then all you need to do, actually I'm not logged in, let me just log in with something or other. Basically, if you log in, you can find the flashcards by going up here, clicking on flashcards, and basically these flashcards cover all of the course. So, for example, if you are doing AQA, let's have a look at one of the topics, like electric fields, or maybe let's go for turning points. I've got various flashcards here for all of the bits of turning points as well. And if you've got a school subscription, sign in, you get all of those included with that. Okay, all good? Oh my God, we've got so many questions. A narrow beam of light is incident on a sheet of Polaroid material. So here's the Polaroid and here's the light. The intensity is a maximum. When the sheet is rotated through 90 degrees, it goes down to 0. So that means this initial light must be polarized. So maybe you've got polarized light that comes in. It's initially going through something like this, so it all comes through. When that filter goes through 90 degrees, basically whatever we see on the other side this plane of the polarization can't get through, so we see that, which is nothing. So the incident beam is polarized, and as it's rotated, it absorbs the light. It doesn't change it because that stays the same, and therefore the answer for 14 is C. Okay, let me just check some messages. Okay, right, all good. Yeah, basically, if you don't know the login, speak to your teachers. They'll have it. If they don't have it, they can email me and I'll email it back to them. Okay, right. The speed of light in glass of refractive index 1.4. So we know that basically refractive index is a measure of the speed of light divided by the speed of light in that material. Okay, now that means the velocity is going to be equal to c over the refractive index. And the refractive index is normally bigger than 1 because the velocity is going to be smaller than the speed of light. So here that's just going to be 3 divided by 1.4 because we know that's already 10 to the 8. So 3 divided by 1.4 is 2.14, and therefore the answer must be part B. So that one there, you didn't need to put 10 to the 8 because you know that's 10 to the 8, and this is just going to speed up the maths to give you an answer equal to B. Well done, everybody. So we've got Paperlitical, we've got Parshama, we've got loads of new people joining actually. This is brilliant. Right. A stationary wave is formed by two identical waves of frequency 200 Hz travelling in opposite directions along the same line. If the distance between adjacent nodes is 0.3, what is the speed of each wave? So if you've got a stationary wave and you've got different nodes, if you think about the positions where the wave might be, okay, if you've got a node and a node, that must be equal to half a wavelength. So if the distance between two adjacent nodes is 0.3, the wavelength must be 2 times that, which is 0.60. And then, of course, we can just use a normal wave speed equation. V or C equals F lambda. So that's going to be 200 times 0.6, which must be equal to 120. And therefore the answer is B. Excellent stuff. Where on the website is this paper? If you go to PMT, I can't remember exactly where. Yeah. For that last one there, you could have put 3 times 10 to the 8, and that would have given you an answer of 2.14 times 10 to the 8, which is what the answer is, basically. Okay, right, number 17. Okay, how can I explain this? So we can use the equation for this one. So my voice has started to get a bit more croaky, so hopefully it'll last until we get to the end of the session. So the frequency for the first harmonic is equal to 1 over 2L times root T over mu. Okay, so that's going to be the frequency of the first harmonic. The frequency of the third harmonic is going to be equal to 3 times this. Okay, so the frequency is equal to 3 over 2L root T over mu. Okay. It then says the length of the wire and the tension in the wire are both doubled. So that's basically what we had initially. And so what we now have is we've got something where... Oh, actually... Okay, let me see. So... the new third harmonic is formed. So basically for here, this new third harmonic, the frequency is going to be equal to 3 over 1 over 2L, but L is double, so that's now going to be 4L times the square root of the tension, which is now 2T over mu. Okay, so basically the first one we've got 3 times 1 over 2L, so that's basically equal to like 3 over 2. And this one here, we've now got 3 over 4 times root 2, so 3 times root 2 divided by 4 is equal to like 1.06, but I should write that better as 3 root 2 over 4. But actually what it's going to be is, if that's the third harmonic, the first harmonic must be a third of that, which is equal to root 2 over 4 compared to 3 over 2. Okay, so how this is probably explained really badly. Let me get just another bit of paper. So the first frequency we can say is proportional to 3 over 2. The new frequency, F2, is going to be equal to root 2 over 4. And so if I divide both sides by 1.5, what's the best way of explaining that? Well, I guess that's equal to... this is not a nice one, is it? Yeah, this one here, if this is an exam, I'd just move on and just keep going, basically. So I would say, basically, if we divide both by 1.5, that means F1 is equal to 1, and 1 over 4 divided by 1.5 would be equal to root 2 over 6. So the answer is C, but I haven't got a good explanation for that. It's kind of like, is there a faster way to do that? Let's have a look. So initially, okay, so basically initially, the first frequency, so the first harmonic for the first thing is going to be equal to 1 over 2L root T over mu. The frequency of the new one, of the new first harmonic, is going to be equal to 1 over 4L times 2T over mu. No, that's not it, is it? Yeah, basically, yeah, there's definitely a quicker way to do that. And I think Macy and other people have probably got the much better idea than I do. So maybe I'll come back to that at the end with a better thing. Basically, I know that's the answer, but my working is all messy. So yeah, basically just ignore number 17. Let's keep going. Which of the following statements about stationary waves on a string is correct? Energy is transferred from the source to the fixed end. No, it's not. So that one's incorrect. All the points on the string between two adjacent nodes vibrate in phase with each other. Well, that bit is actually true. So basically, if you think about a wave that might look at like that at some point, all of these points move up at the same time. So these bits are all in phase. These bits here are all in phase with one another, but all of the bits here are all moving down at the same time. And of course, I guess you'd have all of the bits over here would be all in phase with these bits as well. So this bit here is true, and therefore the answer for 18 is B. Okay. Right, the next one. 19. I'll come back to 17 at the end. Yeah, I might try and do... I'm hurrying up as much as I can. I've got like another 12 questions to go. Right, so Thomas Young's double slit experiment, he used sunlight passed through a pinhole in his window into a darkened room. So he had a single slit, and then a double slit, and then the screen. So why is it that we had a narrow single slit? Basically, it was to make sure that all of the light hitting this was coherent. So any light that comes through this must basically diffract from a single point. And that means the light hitting these is going to be coherent, so perfectly in phase, and therefore A is the correct answer. All good? A, yes. Right, 10 questions to go. Let me have a little sip of water, and then we'll keep going. Okay, this one here is about light from a double slit, and therefore we can use the equation. I'm just going to check the way that AQA give this. They give it as W equals lambda D over S. Okay, all good? Right, so if we've got red light, so we're going to change the wavelength, and the sources are going to be a different distance apart. Basically, the distance to the screen is the same, and therefore W is going to be proportional to lambda over S, I would say. So basically, we just need to look at this number to that number. So we've got, actually I'm not even going to do the first one because that's a very small number, and so that means W must be very small. So I'm going to ignore that one because that's in nanometers. We're going to do the ones in millimeters. So we've got 20 millimeters divided by 50 is 0.4, and then we've got 10 divided by 200, which is 0.05, because we know that basically for this one to save time, that number is in nanometers, so the answer must be incredibly small, and because I've got just the ratio of these two distances in millimeters, that's a bigger ratio, so therefore B is going to be the answer, because these ones are going to be furthest apart. Okay, so we've got trolley A and we've got trolley B, is that right? So a constant force is applied to trolley A, pushing the two trolleys together. The contact force that trolley B exerts on trolley A is a single force, so I'm going to do that as that force. What is the equal and opposite force that completes the pair described by Newton's third law? So it's going to be that force there. So basically, that's the force of object B on object A. So this must be the Newton's pair of the force of object A on object B. So the force that trolley A exerts on trolley B is going to be the thing that is the other force to B on A, so therefore D is the right answer. So don't forget, Newton's law Newton's third law is about the interaction between two different objects. An object of mass 5 kilograms falls vertically through the air. What's the acceleration of the object when the magnitude of air resistance is 40 newtons? So we've got a downwards force and we've got an upwards force. That's equal to 40. The downwards force is going to be 5 times 9.81, which equals 49.05. So the resultant force is going to be equal to 9.05 newtons. And of course, we know that A is equal to F over M. So that's going to be 9.05 over 5, which equals 9. No, is that right? Oh no, sorry. 9.05 divided by 5 is equal to 1.81. So here the answer for that is C. So what I did was I didn't look at the numbers. I drew a diagram to show the forces. I worked out the resultant force and then did A is equal to the resultant force divided by the mass, which is 1.81. Okay. Here we go. So I'm going to work backwards. We basically got initially V equals 0, and at the end V is equal to 0, and in the middle V is equal to a max. And we know, of course, if you've got a displacement time graph, then we know that the gradient is equal to the velocity because it's equal to distance divided by time. So we need to have something where basically initially the gradient is equal to 0, and at the end the gradient is equal to 0. And looking at these, that's got a constant gradient, so it's not that. That's got a positive gradient here, so it's not that. That's got a positive and a negative gradient, so it's not that. Here, we've got basically 0 gradient at the start, 0 gradient at the end, and we've got the maximum gradient in the middle when we've got the maximum value for velocity. So that's why 23, the answer is B. B, 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 B. Sorry, I should have zoomed out a bit. Apologies. So there we go. So yeah, people are saying that we've got Paperlitical, SGL, we've got, is that Shireen, there's Lam, we've got Kyle, we've got Redders, all of you saying B, good stuff. Body X moves and is completely inelastically collided with stationary body y, which means afterwards the two things move off at a combined velocity. Now, of course, initially u is equal to 0, and these two things are the same mass, but now their total mass is equal to 2m. So what's going to happen is that the two objects, well, actually it can only be one of these, they both move off at a combined velocity here. Now, one of them isn't still, so it can't be this one or this one, and they can't be moving in opposite directions because it's a perfectly inelastic collision, so it can't be that one. And therefore, this whole thing moves off. Now it's got twice the mass, moves off at half the velocity, so the answer for 24 is A. Okay, right. Okay. Oh, I noticed this one because the graph scale was a bit off, because basically that's 4 units, that's 4 units, and that's 2 units. So it looks a bit weird, but basically we know that the change in momentum is going to be equal to the force times time. So it's the area under that graph. So you've got 10 times 4 divided by 2, which is 20. You've got 4 times 10, which is 40. And then we've got 2 times 10 divided by 2, which is 10. So the total distance, and I've checked that these are in forces in newtons and time in seconds, the total is equal to 70 newton seconds. And therefore, if the ball is initially at rest, mv is equal to ft. So v is going to be this impulse of 70 divided by the mass of 2, which is 35, which is equal to part D. Is that right? Let's have a look. Sorry, I'm just going to check my answers. Yeah, D is correct. Didn't even need a calculator for that one. So basically, the change in momentum is equal to the impulse, which is equal to the area under the graph. And if you know that, you can, because we know it's initially at rest, m times v is equal to this impulse, so the answer is D. Right. Here we go. 26. Okay, so let's think about what's going on here. So a uniform bookshelf has a mass of 20 kilograms. It's got a height of 1.5, and a child pushes on this with a force F at a distance of 1.5 meters. There's also going to be, in this other direction, if the base is 0.5, then this distance is 0.25 meters. And the force down, due to the weight of that object, is equal to 20 g. Okay, so basically, what we're going to think about is the anti-clockwise moments being equal to the clockwise moments, and that's when it just about tilts on this front edge, which will be the pivot. So, F times 1.5 is equal to 20 g, or 20 times 9.81 times 0.25. Okay. Cool. Yeah, it's a bit more speedy now. Is that okay, Redders? Hopefully this is all making sense. So basically, we've got 20 times 9.81, 20 times 9.81 times 0.25 divided by 1.5 is a force equal to 32.7. And basically when the force is bigger than that, that's when it's going to start to tip. And therefore 26, the answer is A. Is that right? I halved it because basically the shape of that unit was like this, and it's 0.5 meters for the base of this bookshelf, but the weight is going to be acting from that central point, which is 0.25 meters from the edge. Okay, so we've got this force acting at 0.25 meters. Okay, is that right? Cool. Two identical springs, each with a spring constant K equals 400, are arranged in two separate configurations. In X, so we've got springs in parallel, and in Y, we've got them in series. Okay, so basically here, imagine it, if we were to apply a force onto this, they'd only extend by half the amount. So effectively, we've doubled the spring constant to 2k. If we put the same force on this, the top one would extend, and so would the bottom. So the effective spring constant goes down by half. So the ratio of this to this is basically 2 to a half, which is equal to 4 to 1, and therefore D is the right answer for number 27. Okay, sorry, which comment didn't I see? What's the best thing to do to get the A star while being on a B or an A? Number one, come to my masterclass on Saturday. That will definitely help, I reckon. Do all the past papers, and then just keep doing question after question after question from whatever past paper you can find. It could be old spec, could be some OCR ones, some EdXL ones. Just keep doing physics. Okay, yeah, hopefully that's all right. These papers are PMT ones. I'll put the link in the description underneath after the session. Right, number 28. I couldn't do this one initially, but then I found it's not actually that bad. So 28, this is going to be the question that most people find difficult. The first thing I did was I drew the circuit like this. Okay, so here we've got the thing where we've got an EMF equal to 12. The internal resistance is equal to 2. And the power here is equal to 16. Everybody good so far? All about this? Right. So basically, let's have a look at this. So what is the value of R? So there's two equations we can use. The first one is that P is equal to IV. And the second one is that the EMF is equal to V plus IR. Okay, so we've got an EMF of 12 volts. The internal resistance is 2 ohms. We've got a power of 16 watts, and we want to know what the value of V is. So basically the question is, what the hell is V? Yeah. Could you let me know if there's any kind of huge collection of model answers to written questions which are repeated over and over? I guess it's a good question. I do have lots of model answers. I've got answers to AQA paper 1 from 2024, 23, 22. I've got paper 2 and paper 3 and lots of the optional ones as well. So I've got loads of stuff on my website where you will see like model answers to just question after question after question. Okay, let's put some numbers in. So the power is equal to 16, and that's equal to I times V. And also the EMF is 12 volts, and that's equal to V plus 2I. Okay, so what I've got here now are two equations. So we've got the EMF is equal to the terminal PD plus 2 times I, because R is 2. And also 16 is equal to IV. So what I can do is I could also say that I is equal to 16 divided by V. And I could then put that into this part of that question over here. So we could say that 12 is equal to V plus 2 times 16 over V. All good so far? So now if we multiply the V up by both sides, we can say that 12V is equal to V squared plus 32. Or we could say that V squared minus 12V plus 32 is equal to 0. Okay, so now we've just got a lovely little thing where we can put this and solve for V. So again, I'm going to ask everybody here, what is something that multiplies together to make 32, but they add together to get minus 12? So what are going to be the numbers over here? So here we go. What do you reckon? So we've got minus 8 and minus 4. So you've got minus 8 and minus 4. And that means to solve this, either V is equal to 8 volts or V is equal to 4.0 volts. Okay, so that's the answer. It can either be one of these, a high voltage and a low current, or a low voltage and a high current. And therefore, the answer for 28 must be 8 or 4, and 4 is not an option, so 8 must be the answer. So that's my answer there for part C. I don't think you would get a question this difficult, fingers crossed, in your real exam next week. But basically, this was my approach to number 28, which I thought was actually a relatively okay question if you've got lots of time to think about it. So we've got a couple of simultaneous equations, do all of that good stuff, and get the answer. Right, there we go. Cool question, maybe. Right, let's see. I think we've got 3 more questions to go. This has gone forever, hasn't it? I've been at over 2 hours. By the way, if you've been here the whole time, incredible stuff. So, a filament lamp is connected to a power supply and the PD across it is gradually increased. The current, they draw an IV graph. Okay, so we get a shape like this where you've got I and V. So what's the shape of the graph? It's a curve with a decreasing gradient. So it's not A or B because the gradient is decreasing. The reason for that is that the resistance increases because when you've got a greater current, you've got a greater heating effect, greater temperature, greater vibrations in the lattice. So the resistance increases, and therefore C is probably the right answer. Right. Yeah. Somebody says they just grind out past papers. Honestly, it will help. You just got to keep doing it and just trust the process. Okay, 30. Oh, I've got 3 more questions still. Yeah, I'd say if you're doing lots of past papers and you're not improving, a good point there that somebody said, Marlo said, is basically you've got to really focus on the marking and reading the examiner reports and then putting that into practice next time you do a past paper. Oh, right, so this one here, SHM, the total energy is 1.8 joules. Okay, how am I going to do this? So, right, so basically, if we know the kinetic energy, that's equal to a half mv squared. So the velocity at that midpoint is going to be equal to 2 times the kinetic energy over the mass, square rooted, which is equal to 3.6 over 1.2, and the square rooted is equal to the square root of 3. Is that right? Okay, we can now look at the equations. Less sighing, more applying. Yeah, sorry, you're talking to me for sighing when I see this stuff. Okay, so we know okay, we also know that Vmax is equal to omega A. So omega is going to be this value for Vmax, which is root 3, divided by the amplitude 0.15, which is 11.54 radians per second, and V is equal to omega multiplied by a squared minus x squared. So that's going to be the same. I'm going to do it under here. 11.54 times the square root of let's say 15 squared minus 0.15 squared minus 0.09 squared. So let's see. That's about 1.385. So therefore the closest answer to that is going to be the first one, which is A. I thought that's too much work for 1 mark. Yeah. Should you repeat all the past papers after doing them for your week topics? Yeah, definitely. Yeah, cool. Yeah, just keep doing past papers. It's like you learn so much, especially when you analyse the mark schemes and the examiner reports. Right, so this one here, we know that for a pendulum, T is equal to 2 pi root L over G, and therefore T is proportional to root L. Okay, so the length of the string is reduced so the new length is exactly a quarter of the original length. So that was the initial conditions. The new time period is going to be proportional to the square root of L1 over 4. And therefore you've got the square root of that means that T2 is going to be proportional to root L over root 4, which is equal to root L over 2. And of course root L is proportional to T, so it's basically going to be half of the original value. So 31, I think the answer is C. People like the Lego man. This one here, how cool is this? Also, if you take off his head, there's a little Lego man inside driving the big Lego figure, and in his backpack, in his air tank, sorry, there's another little robot that's kind of hidden there. So there's some, this was like a lovely bit of Lego I bought recently. I also ordered the Tintin rocket, but it's out of stock and it hasn't arrived yet. So I'm a bit disappointed. I've ordered it over a month ago. Right, the last question. Okay, damping. So this is what you get normally, and then it says, okay, so I guess if something's damped, it's going to go down like this, and what we find is that the frequency, or its natural frequency, basically goes down at a lower amplitude. So which statement correctly describes how the damping affects the system's responses? It doesn't eliminate the natural frequency, so that's not true. It doesn't increase the natural frequency, it actually makes the value for F0 smaller than it was before. Damping reduces the maximum amplitude, that's true. It doesn't change, well basically aerodynamic flutter isn't on the spec, so it can't be that one. And basically the answer for that is C. Oh my god, there we go. A little bit of SHM, bit of damping, all good stuff just to finish off that topic. Right, I can't believe I've been talking for so long. My voice is definitely getting a bit hoarse. Basically, it's been great to have so many people here. We did it. Right, just to remind you, as it says down here, obviously this is a completely free thing, 2 hours doing one whole paper. Hopefully some of that was useful. I know it's like a long thing to watch, and I'm amazing to see so many people here, like Macy, Redders, Kyle, so many people here. I think Kyle, well, he was in my class before this as well, so I think I've been talking for like 2.5 hours now. So yeah, that's a lot, 3.5 hours of physics. Basically, if you want to hear even more, hopefully my voice gets back to normal, I'm going to be doing classes next Sunday. Make sure you book them now, get them in the diary. I'm doing classes for paper 1, paper 2, paper 3A as well. So hopefully that's all good. Yeah. Also, good question. Do you do paper 2 and paper 1 revision? I would say just do paper 1. Just keep focusing on paper 1 for the next week, and then you've got plenty of time before paper 2. Right, everybody. Good night. I'm going to call it a day there. And yeah, hopefully all of you just do lots of work, do pass papers, go to my website, buy some stuff, and sign up for masterclasses. And I'll see you